Okay, welcome everybody. I just thought I'd start off. I've been clicking around looking at the next week. We will be doing the interesting things. Next week we'll be looking at data. You will be looking at examples at websites, at newspaper stories, and saying what is wrong or right about the way the data is presented, or how you might do it better. You'll be sort of taking apart the way that statistics is used in today. And so we're collecting data sets and examples, and we'll start on that next week. But just, I'll be making a list of these, but I've just been looking at some sources, places which now really use data. And one I know about is an English newspaper, The Guardian, which has got this thing called Data Blog. Facts are sacred. So facts are sacred, it says. And they just specialize in infographics. You see things like this, pictures of data. But they also provide all the spreadsheets, the .csv files to read them in. So the data that they provide, we can look at as well. So if we look down through the last few days, what they've been putting up, we immediately see one here. This is quite an interesting infographic. This is about US aid from the UK. Here we are, where Britain's aid goes. And that's right. I'm probably get full screen. Oh no, where's it gone? What have I done? How can I get that looking nicer? Oh, that's not too bad. Anyway, so they're showing that Britain gives aid to various countries, and but the use of graphics is quite interesting. So first of all, they're using spatial maps. How are they using the size of the blob? What does the size mean? It's the amount, yeah. And proportional to the area, they're getting that right. So that it's not the diameter, it's the area is the size. They're not using colour at all. They're not using, I'm not quite sure what they could use colour for. But then we've got, so we're using a spatial map, we're using size, then there's bar charts. Bar charts to show trends. This is over years. I think this is 2006, 7, 8. So this is a year showing a trend. Not a line. They could join those up. But so bar chart to show trend. And then here, another bar chart to show this is the aid from different countries. Oh, I can't. I'm going to see if we can wind this down a bit. Oh, there we are. Oh, God, I can't read them. That's a good chance. There's Germany, UK, France, Spain, something like that. The amount of aid as a percentage of GDP or something like that. So we see there's, it's quite there's a lot of numbers there, quite visually. What do you think of this? Is that quite good? Yeah? Might be able to do better. So anyway, so that's the kind of thing that they've got. So they do maps of schools, education at daily air pollution levels across Germany. Sounds pretty dull, but never mind. Insulated homes, Sheffield students, charitable giving, bike journeys, cycling in London, where do the bicycles go in London, etc. So we can see there's lots of data sources, and the other one, I think the New York Times does a lot of this kind of thing. So we'll come on to those later. Here's one I found about Uganda. In fact, this is about how spending in Uganda, where they show a total amount, 2 billion being spent in Uganda at the moment on education, public administration, roads and works, public sector management, security. So that's the sort of Ugandan budget. But what you can do, and this is quite cool, if you move over to education, you can blow it up, and then you see how much is going on primary, secondary and tertiary education. Then, so that's, again, they're using the area as proportional to the budget. Very nice graphic. Using movement, showing the breakdown. Then also they're using a pie chart, essentially, to show what proportion is from domestic spending, from budget support and aid projects. So they're showing what the source of the funding is for those as a pie chart. Not very good colouring. I don't think it's very... Colouring, you can't read it, can you, very well? All the colours are the same. So it's a shame. But you see they're using area, using a pie chart, etc. And then, don't know if I can go down even further. No, that just seems to go round and round in circles. Whoops. So, I'm not sure what the point of that is. But it does go round in circles. And then I can go back to the main one and look at security and what security armed forces being 195. Well, that's quite good, isn't it? You try to catch it and it whizzes around in the zoo. I think that's a bit silly, really. But so you can see this is, basically this is quite a simple data set, but one where they're using the movement to attract attention. Okay, so we'll come on to some of that later. All right, so next week we'll be getting you to look at some of these, find some examples, take them apart, do a criticism of them. Okay, now, right, back to work. Back to work, right. We've got to do a bit more. We've got two, essentially, today we're going to do estimation, confidence intervals and fitting lines. Tomorrow we'll be doing hypothesis testing, p-values, testing for differences. And then we'll have sort of, covered the basics. So, and that leaves then next week to use some of these tools, some of the graphs and the estimation to look at examples. So we'll have 2 more days of this this material. Right, okay. Back to the proper work. We're back to the mathematical thing, a set of independent and identically distributed random variables x1 to xn, each one with the same density, for some unknown parameter theta. We've seen how we can calculate a maximum likelihood estimate of theta. We take the logarithm of the product of those, differentiate. And we've seen also how we can get the variance of this, or at least estimate that, the variance, the maximum likelihood estimate. And the square root of the variance of the estimate is known as the standard error. The standard error is how accurate our estimate is of the quantity we're interested in. And we usually assume that our estimate is normally distributed around the true value with this variance. Now, what we want to do is, instead of just getting a single number, as we've done so far, we're calculating some number. We think this is our estimate. We want to say, well, how certain are we about it? We want to create an interval. And we want to create an interval such that we're 95% confident it's in there. Or we might have a shorter interval. The other one we're going to look at is one where we're 68% confident. So it's like 68% is that we think it's almost twice as likely to be in there as outside. So 68 is in and 32 is outside. Whereas this, we think we're really confident it's going to be inside. So we want to create some sort of interval. And we do that by taking the estimate and doing plus or minus c times the square root of v. So this distance here is c times the square root of v. So it's c standard errors. And in fact, it turns out, for 95%, c is 1.96, or essentially 2. And this one, c is 1. So what people usually do is produce intervals plus or minus 2 standard errors, or sometimes plus or minus 1 standard error, sometimes 3 standard errors, really wide intervals. Then you can be really confident you've got the true value if you've done a good experiment. So this is really what a confidence interval is. So we're just going to see those working. Okay, now here's a bit of maths. This is a random interval. It's an interval that we're going to calculate as a function of data we haven't observed yet. So we think of it as a random interval. Okay, here's a bit of maths. See if we can follow this. If I got this right, tell me if I've got this right. The probability this random interval will include the true value is the probability that the true value is in the set, is in the interval. That's the set, which is the interval. Now that, if we rearrange that, it's the probability that the lower end of the interval is less than the true value and is less than the upper end of the interval. So that's what we want the probability of. Now we can rearrange that. If we, for example, add that on to there and subtract that onto there, we get an interval now in terms of the estimate. It's the probability that our estimate is in the interval the true value plus c square root of v and the true value minus c square root of v. Now we can take, from each side we take away theta naught, divide by square root of v, and we end up with this. But we know that we're assuming this is the case. And if that's the case, if we subtract theta naught and divide by the square root of v, now, okay, why is this the case? Why is theta hat minus theta naught over square root of v, that is a standard normal. Now, what's the best way? Who can explain that? Why is that the case? Anybody want to explain why that's the case? Well, we know that theta hat is normal theta naught with variance v. What's the easiest way to say, well, therefore this is true? Because there's a number of ways to do it. Maybe we want to change the variable from this to this. And so maybe actually the easiest way to think of it is that expectation of theta naught is theta naught, theta hat is theta naught. So that means the expectation of theta hat minus theta naught equals naught. Because we know that subtracting from an expectation subtracting from a random variable subtracts from an expectation. So, and also then, we know that the variance of theta hat minus theta naught is v, because subtracting a number doesn't influence the variance. So therefore the variance of theta hat minus theta naught over square root of v equals 1, because remember, when you put in a multiplier, you square it when you take it outside. So that's it shows that the mean and variance will be 0 and 1. And I think it's probably the easiest way to remember it, that we do that. We could do a full change of variable is an alternative way to do it. Okay, so that means that, this is standard normal. So the probability this random interval includes the true parameter value. Remember this phi, this is the phi function, is this area. So if I've got minus c, this is phi of minus c, and if this is c, then that is phi of c, is the tail area to the left of, this is a standard normal n01 variable. So phi c minus phi of minus c, well actually we have this identity which I don't know if I've made clear. This is all symmetric. And so phi of minus c, this is a good thing to remember, phi of minus c, which is this small area there, is 1 minus that area. So this is, if one just, I always have to draw it to remember this. Really useful. 5 minus c is 1 minus 5c. So then we can immediately just plug that in, and we get 2 phi c minus 1. Okay, so for a 95% interval, c equals 1.96. For a 68% interval, c equals 1. Now, so that means that if I calculate these intervals lots of times, 95% of the time, if I use this, it will contain the true value. In practice, we calculate a single interval and say we are 95% confident the true value lies in the interval. Strictly speaking, we should not say it's 95% probable the true value lies in the interval. We should use the language 95% confident. Okay, so that's it really. Right, what do we do then? Now, if in many cases we estimate the parameter by a sample mean. In the normal, we've seen in the Poisson, all sorts of examples, we use the sample mean, not all of them. And in that case, we know that the variance of x bar is the variance of x1 is 1 over n, over n. The standard result that the variance of the sum over n, which is 1 over n squared, variance of x1 plus the variance of xn, which is n times the variance of x over n squared, which is sigma squared over n. So that's the standard result, that the variance of a mean is the variance divided by n, the variance of each observation divided by n. So the problem is that often this is unknown. We don't know what the standard deviation is of the data. Now, if this is unknown, there's a more precise theory based on t distributions. Though I'm not going to do it in this course. People may have done it already. People done t distributions and things? Have done that? Yeah, I thought some of you might have. That's fine. We're not going to do it. You can ask them. If you, but it's some standard work, but it's only for small samples. Only for small samples. And it doesn't work for more complicated examples. So in general, we're going to have to approximate this variance, usually by 1 over n times the Fisher information. Approximations for large samples. Okay, so now, in this first part, we're going to do a little test on confidence intervals. So I'm going to get you to do a little exercise to show about calculating an interval and see what happens. Okay, so the exercise is based on our heights. Now, let's say we wanted to estimate the mean height of everybody in the room, your average height. Now, in fact, we know it because we've got it. And we've got the data on your individual heights. So based on 50 people, we can get we know the estimate. But let's say, what about if we only had data on a few of you? How would we calculate? How well could we estimate the height? And would we know how well we could estimate the mean height? So what we've done is, or what Adrian's done, is to produce, we've got all your heights on little bits of paper, and I want you to take out, in groups, just on each table, 5 of these heights at random. And Emil has very generously lent us his hats, many of his hats, to pull the data out of. So each table, you should pull up 5 heights. Then, calculate their mean. If you have a calculator, do that. Otherwise, it's only taking the average of 5 numbers. So I think you can do that. So calculate their mean. Now, we've said that an interval. What I want is an interval around these values that you're going to get, each one based on only 5 observations. So I want you to calculate an interval. Now, to do that, we need to know the standard error. And the standard error is sigma over root n. And I'm going to tell you that, in fact, the standard deviation of your heights is 10.1. So your heights have a standard deviation of 10.1. So the standard error is 10.1 divided by the square root of 5 is 4.52. So a 1 standard error interval, that's with 1 in there, is just your mean plus or minus this. So what I want you to do is calculate your mean and add on plus or minus, well, I needn't have the 2, 4.5 centimeters. And you'll then get 2 numbers. You'll get 1 number in the middle, sorry, 3 numbers, 1 in the middle and 1 on each side. And then what I want you to do is to come up and draw your interval on here. So you might end up with something, like that. And another group might be like that, or something like that. So I should end up with a lot of intervals on here. Ta-dang! It's finished. So what I want to end up with is a lot of intervals on here, and to see what they look like. How many? I won't tell you the true value yet. We're going to try to guess the true value from where the intervals are. I can't remember what it is. So is that okay? All right, you're off. Oh yes, when you take the 5 out, put them back in again. It's sampling with replacement. Otherwise, we'll lose all the hats. So, here we are. Emil's hats. I have them already prepared. Can you help take them round? It's very generous, right? Can someone? So each table, take out 5 and write them down on a piece of paper. Just write them down and put them back in the hat, quick. So this is like you picked 5 people at random from the room. Well, just do one. Yeah, let's get them onto the next table. Just do 1 per table. Okay. Yeah. I think otherwise it'll take too long. I think. Yeah, I think I made my scale too big, haven't I? I'm going to change the scale, quick. Right. First one. Yeah, use the white, I think. Yes, no need to write on the expired. I think just put the. Yeah, don't need to. It'll get too big, I think, if you write it on. So just put a big blob or something like that. Yeah, maybe. What should we do? Maybe do a. Maybe get people to. Yeah, so we can see it. Yeah, put a blob like that, and then a line at each end. Yeah. That's it. Lovely. I think I'll take these out off so we might need to fit some more on. Oh.
What is C in this case?
What is the
C?
Oh, it's just 1. Yes, I should have said. Oh, yeah, C, because there's I haven't put it in there. Yep, it's there. It should be there. So it's just 1. So it's a 1 standard error interval. So there should be a 68% probability of it containing the true value.
How do we calculate C? By giving percentage.
Oh, you forgot. Oh, yes. From the normal tables. Yes, it's a good question. You need the it's the Q norm function in R, I think, like that, where you put in a number. Oh, I'll find that. You put in a number like 0.95, and it'll tell you what C to use. But the standard ones are 1 and 2, really. C is almost always 2.
But if you don't do these things, you can't find the C.
Well, it's just a standard thing to use 2, to use C equals 2. That's become a sort of convention. There's no correct value. It's more just what people usually do is usually report 95% intervals.
But I think the significant variation it depends by group for find the C. It's the same on all.
People usually use the same one all the time. Yeah, they usually use 2. It's the sort of standard interval is to use 2. It's just by but usually use 2. I'm using 1 here because I want to have the intervals a little bit narrower. But people usually use 2. The phi function isn't available in closed form because phi. Phi of C is the integral between minus infinity of C and 1 over root 2 pi e to the minus t squared over 2 dt, and that's not solvable. You have to use tables or a computer algorithm. You can't solve that.
Squares.
Sorry?
That is the 2 squares, exponential minus 2 squares.
Yeah, t squared over 2, yeah. So it's the error, like the error function. You can't solve that in closed form.
Squares p divided by squares 2.
Yeah, you can't do that integral.
That is a function of C?
Yeah, there's a function of C, because C is the top end of the integral. So it's a function of C. So this equals equals sort of 0.025 when C equals minus 1.96 equals 0.975, C equals 1.96, etc. So it's just, and we'll do that. You can just get that from R or any program, or on some calculators. Okay.
Basically, what you do when you have 2 phi of C minus 1,
yeah,
which is equal to 95%.
Yeah, you solve it.
You solve it and
you get C.
Phi of C.
Exactly. Yeah, exactly.
In real situation, no one is given which interval to use. So
No.
I would like to know what can I maybe base myself on.
This is purely, it's like a convention. It's a habit. It's what people generally do is 95%. Sometimes they'll do 99% if they want to be more confident. But the two ones usually used are 95 and 99. And so if you read a scientific paper, they're almost always 95%. All the medical papers, I think nearly all of them are 95% they'll use. Just from convention, really. It's just traditional. It's just traditional, really. You said 95% sounds, it's not 100, but it's quite a big number.
Why do we assume that theta follows the normal distribution?
Well, that's all right.
Distributed?
If it's because of the central limit theorem, if you're using if it's a maximum likelihood estimator, then it is asymptotically normally distributed.
What do you mean asymptotic?
Well, n. Oh yeah. N. I don't know, 50 observations maybe. Sort of.
Many observations.
Many, but more than about 20 or 30. Things below that, you have to be a bit more careful. But above about 30, then it's like infinity. It's like asymptotics. So, yeah.
I don't really follow what the meaning of normal distribution. We know that binomial is the sum of Bernoulli's.
Yeah.
What does the normal distribution do?
It just appears in many. It arises because of the central limit theorem. Lots of small factors influencing produces a normal distribution. That's why people's heights are normal, because the influences on your height, there's many small influences on your height. Your genetics, your diet, your parents, all these things influence your height. So
take into account many different
things, you get a normal distribution coming out. Automatically appears. So it sort of it happens in nature a lot. It's the sort of law of error, they called it. It's like measurement error as well. When you're trying to make measurements in astronomy, things like that, they end up being normally distributed because there's lots of different things that could affect them.
For example, coins doesn't follow.
No, not unless you do lots, because the binomial tends to the normal. So no, it only applies for very rare events. For common events like flipping a coin, it tends to a normal, and so the number of heads ends up looking like a normal distribution. After about 30, 40, something like that, the binomial looks normal after about 30 observations. It starts looking normal. So asymptotics is 30, I think, roughly. Yeah. Okay. Actually, it's break time. So when you just, I need a cup of tea. So we can have a break now and come back and have a look at this. There's not even an overlap there. Amazing variability. So we've got 20 intervals. Where do you think the true value is? It should be somewhere in here. Now, and what should happen, these are 68% intervals. So in theory, there's a 68% probability that it will include the true value. So we should have, so how many should include the true value? How many would we expect? Out of 20? About, roughly? Sorry? 13, yeah. I think we should expect about 13. So we expect, it won't be exactly, but we expect 13 to include the true, no, what is, does anyone know? Hang on, I've forgotten. I've forgotten. Hang on, let's have a go. Let's ask for mean and height. And what do you think it's going to be? What do you think? 100 and... Guess? 1/6? It's mean. This shows it's got missing values, so it won't calculate the mean. So what have I got to do? I've got to do mean NA dot omit height. Right, omit. Now that should. Do you think this is going to work? Hey, 167.6. So you should have got a prize for that. So 168 was the true value. So it's there. So that's the true value. So let's go. Now this is not precision science, but okay. Let's go up here. Oh, somebody got it almost dead on. Now, how many include 1, 2, 3, not that one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, well, 16. That's more than we might expect. That's okay. 13, 16, it's statistics. So, and if we had done 95% intervals, would have been wider, then they almost all should include the interval. So that shows, yeah, that's quite good. So the idea, okay, what happens if each of you had, instead of choosing 5, you had taken 10 out, what would be the effect? What would happen to these intervals? Yeah, they get narrower. How much would they get narrower by? What would they shrink by? You double the sample size, what would they shrink by? No. It's not, they're not half the width. If you double the sample, no. Yeah, but it goes down by this. But remember, it's sigma, these are x bar plus or minus c sigma over root n. So if I double the sample size, what happens to the width of the interval? Yeah, it gets smaller, but by how? But what? By what fraction? Sorry? It's like a 2. I put 2n in there. Yeah, exactly. It goes down by 1 over root 2, which is about 70%, about 0.71, I think. So if you double the sample size, these will only get smaller, these will get about 30% smaller. But not half the width. So if you do a survey of 1,000 people, and then you do a survey of 2,000 people, your intervals do not go down by half. They only go down by 30%. So, so that is supposed to illustrate the idea of if you did more, these would get tighter. And they should get closer as well to the middle. Okay, so that shows that these intervals are random intervals. Now I think, I'd just like to explain again about the C and the phi. This is quite important actually, so I'll draw it up again. This idea that we have a normal distribution there, standard normal, and then we have that's 0, and roughly that's 1, 2, minus 1, minus 2. And then this area is known as phi. It's the area to the left of a point. So phi of minus 2 is about 0.025. It's about 2.5% down there. So that's also 2.5%. So that's why an interval from minus 2 to plus 2 contains 95%. And 95% intervals, it's a convention. It's sort of tradition in science to use 95% intervals. If you look in a scientific paper, in a journal, they will almost always use 95% intervals. Sometimes, we'll talk about this tomorrow, sometimes they use 99%. And sometimes even more extreme. If they want to be really sure, for the Higgs boson, they used 99.999%. Because they didn't want to make a mistake. When you're deciding the laws of physics, you don't want to make a mistake. Actually, I think they did 9 as well. I think just to make sure. They wanted to be really, really, really sure. So we'll talk about that tomorrow when we talk about testing and things like that. So this is the Higgs boson. But generally, people use 95. Okay, is that all right? And so in the practical, we get you now calculating intervals. So the crucial thing is, when you run the models, when you're fitting things, the computer output will give you the standard error, which is this bit here, the standard error. And then to create an interval, you usually use the estimate plus or minus almost always 2. Well, 1.96, but 2 is close enough. 2 standard errors. Okay. Are there any questions on that? Right. Good. Great. Let's go on to a bit of do some fitting. Oh, I've got all the hats here. I don't want to steal Emil's hats. Great. Okay. So we've done that. That's good. Oh, yes. Now, nearly everything we do in statistics is making comparisons. Comparing men and women, comparing different countries. And so comparisons are a really basic idea. So now we're going to do how to put an interval when you're making a comparison. So you're observing some observations from a distribution with unknown mean theta x, and I'm going to assume a known variance. So let's say, you know, height or, so we might be, we've got some data, you know, let's say we got some data on women, looking like that, and we got some data on men that looks like it might be, you know, a bit higher. There's some overlap. We assume these come from some distribution. Are these distributions different? Is there really a difference between men and women? And so this is, you know, the most basic idea that we, in statistics. So we want to estimate the difference between the means of the distributions and provide a confidence interval. Now the first thing is that we will estimate the difference in the population means by the difference in the sample means. So we would just take, you know, x bar there, which would be about there somewhere, and we take y bar there, and x bar minus y bar is our estimate of the difference between the two means. So that's the natural thing to do. But we know that the sample mean has got approximately a normal distribution that looks like that, and similarly for y bar. And this is, whatever the shape of this original distribution, the sample mean has got a normal distribution. Now, the trick is to realize that that means that the difference between the means has also got a distribution, and its mean is the difference between the means, and its variance is the sum of the variances. So this is the, if you remember, you've got two variables. Your expectation of x minus y is just the expectation of x minus the expectation of y for anyone. I'll put the bars in there. And the variance of x bar minus y bar is the variance of x bar plus the variance of y bar. Plus, very easy to make that mistake. You add the variances. Yeah, it's because it's minus 1 squared. Yeah, exactly. So you can think of it as the variance, this is variance of x bar plus minus y bar, which is the variance of x bar plus the variance of minus y bar, and the variance of y bar, that's just the same as the variance of y. So we could think of it like that. Okay, so we add, you subtract the means, but you add the variances. Now it's easy. We've got, this is just a number we calculate. This is what we want to estimate. This is now our standard error. So our interval is just the estimate plus or minus 1.96, c equals 1.96, square root of this. So instead of just one of these in there, we put them both in. It's a really straightforward calculation to do. So, for example, let's do an example. Comparing two proportions. So let's say I wanted to compare, you know, proportion of men, proportion of women. If I've got the original data is binomial for theta and y, and I want to compare the difference in these proportions, estimate the difference in the population. These are the difference in the observed proportions. Now, if you remember, the variance of x is just theta x times 1 minus theta x. No, hang on. Oh, yeah, no. The variance of the Bernoulli, the underlying Bernoulli. Yeah, because this is the sum of n Bernoullis. So this is the variance of Bernoulli divided by the sample size. This is sigma x squared, and this is sigma y squared divided by m. But now, remember this is what we did yesterday. This is fine, except we don't know these. That's the whole point. We don't know what these are. So we have to plug in our estimates in here. Now, okay, that looks quite complicated, and of course, it's best to get a computer program to do it for you. But let's see how that would work in a real example. Okay, let's see. Actually, I might get somebody to help me with this one. Let's see how this would work in an example. Okay, silly example. In the class, out of 18 females, 14 could roll their tongues. Like that. 78%. And out of 31 males, 22 could roll their tongues. 71%. Let's assume this class is a random sample from the population of the Earth. You're completely representative of males and females throughout the world. Yes, of course you are. So you're a representative sample. Next week we'll be talking about when we can assume a representative sample. What's the difference between the percentage of all men who roll their tongues and the percentage of all women? Actually, I've done women minus men. So in our sample, it's 7%. Now, but do we really think? Who thinks that women, on the whole, a bigger proportion can roll their tongues than men? Yes, he believes it. Because we got quite a small sample. If we'd asked, 10 million men and 10 million women, we might believe it. But this is not based on many people. So, have we discovered a new scientific fact that women can do this more than men? Well, okay. Well, we need to plug into that formula. So, actually, does anyone want to have a go? Does anyone want to volunteer? Otherwise, I'll pick on somebody. To see how we could work out a confidence interval for that. Anyone? If you don't want to come up, you've got to tell me what to do. Okay, you've got to tell me what to do. I'll start off by, what's x over n? Yeah, 14 over 18, which is equal to 0.78. Okay, what's y over n? M. Yeah, 31, which is equal to 0.71. Okay, so the first bit of the formula is 0.78 minus 0.71. So our estimate is 0.07. So a 7% difference in the... Okay, now, what's the interval around this? So we want to do plus or minus 1.96. Now, okay, what's the first? What's in here? Yeah, 0.78 times what's in here? 22, yeah. Divided by 18, yeah. Has anyone got a calculator? Because you could go ahead. If someone's got a calculator, can they try to do this? Okay, what's this one? 71 times 29 divided by 31. Okay, so that's a straight calculation now. Okay, is anyone going to try to do it? Otherwise, I'll go. Jeffrey, you're going to do it. Get your phones out. This is about. Let's try to do it in our heads. What's that? That's about.
Yes, the first one is 0. Yes,
What? Which that?
yes.
What is it?
9, 5.
Oh, that's close enough. That's that one, is it? The other one will be similar, roughly the 0.0066. Okay, they'll be roughly the same. So we add those up, and we get square root of 0.0. I can't do that. 116, like that. Yep. Square root of that is about what is it? 0.13. What's the square root of this? Any answers? Well, 0.126. Okay, so we got plus or minus 1 point times 0.126. So that multiplied by 1.96 is about 0.25. So, is that right? So we end up with this interval is 0.07 plus or minus 0.25, which is an interval from 0.32, so what's the bottom end? Minus 0.18. It's a huge interval. We haven't got a clue. It's a completely useless experiment. It's an enormous interval. You know, women could be 32% more likely, right down to men could be 18% more likely to be able to do it. So this experiment has been far too small. The crucial thing is the interval contains 0. In other words, no difference is a plausible value. It's in the interval. So that's one of the ways we can make inferences, is to calculate the interval and see if 0 is inside. It's amazingly wide. I think, have we done the calculations? Right, I think they're right. Do you think it's wrong? It does seem very big. I think we need to check this. We'll check it. But it could be because these are very small samples and it does seem very big. I thought this would be about plus or minus 0.15 or something like that. Anyway, it shows. So I think you can see these are really quite straightforward to do. So any time you see somebody says, is making comparison between two proportions, just got to shove it into this formula and you can say whether the difference is real or not. Okay, now let's do the last bit. Is quite nice. Is doing starting to do further on plotting, on comparing quantities, estimating now a straight line. So instead of just estimating a proportion, so here's height against length of your hand span, and I've chosen those because they're quite nice because they, it looks like. What do you think? Related? Taller people, bigger hands? Sort of. What's that one doing? Anyway, this is a very small person with huge hands. We should be able to see them. This is either a mistake or I might have typed the number in wrong. Anyway, the point is, it's only when you look at the data, plot it, that you see this. I think, is there anybody, you need someone about that tall with hands about this big? Right, okay. How are we going to fit a line through here? What we've done mathematically, we've observed a set of points, x and y, and we want to fit a straight line through them. Now, the first thing which makes things very nice is to take away the mean from all the x's. It makes the mathematics so much easier, makes everything much nicer if we can do that. It's sort of meaning that we're changing the axis to the middle of the axis. That's what we're doing. Not all books, not all explanations will do this. I find it easier to do this. So we want to fit a line yi equals a plus b x minus x bar plus some error. We assume there's some sort of error around here. So what we're saying is we're going to fit a line assuming there's a straight line through here and that each of these is drawn from some distribution with some sort of, we call it error. I want to be careful about that word. The mathematical model we fit is that we assume that these data points, that there is some true straight line, and this distance is known as the error. Now, it doesn't mean a mistake. It does not equal a mistake. Although that probably is a mistake. That probably is a real error. It's just used to mean variability. It's a historical term called error. It doesn't mean mistake, it just means variability. So that's the model we're going to fit, and we're going to assume that these errors have got a constant variance. So we want to estimate. Now we don't know the true values for A and B, so we want estimates for A and B. So we're going to use this notation, yi hat is the fitted value. So if I fit a straight line here, this would be perhaps y1, and that would be y1 hat. It would be the sort of where I would estimate y to be on average on there. So it's the perpendicular projection down to the straight line. Now the distance here is called the residual. This distance is the residual. It's what's left over. It's the lack of fit. It's how much the data points are away from the line. And the solution, which was done by Gauss nearly 200 years ago, was called least squares. You minimize the sum of the squares of the residual. Now, there are methods that, so I'm going to take these distances, some will be positive, some will be negative, and I'm going to square them and choose the line that minimizes that square. There are methods that minimize the absolute distance, the sum of the modulus of yi minus yi hat. But they're much more difficult. Mathematically, they're not as nice at all. They're much more difficult mathematically, in fact. The square works out very nicely. It's also what you would do. These are also the maximum likelihood estimates if we assume the errors are normal. This doesn't assume normality. But if we do assume normality, these are the maximum likelihood estimates. Okay, so bit of maths. Quite nice, really, I think. If you follow this, the residual sum of squares, therefore, is the sum of yi minus this fitted line, squared. So it's the sum of the squares of those. And I want to choose A and B to minimize this. And it's the same as maximizing the likelihood in a normal problem. So again, I'm going to take the derivative with respect to A and B and set them to 0. But these will be, in fact, minimum rather than maximum. Now, when I take the derivative of this with respect to A, the 2 comes outside and the minus sign, and then I take just use the, and this is repeated though without the square. Remember, this is the function of A, so by the chain rule, I just use, or derivative of a function, I take, I don't know how to explain differentiation. I've forgotten. I hope you all know it because I can't teach. I've never taught differentiation. I don't know how to do. I don't know how to do it. Anyway, so and when you see this, when we take the summation inside, we get a sum of yi. We get n of these. The b comes outside. The sum goes in front of there, and we get this. Now this, we see, and just goes to 0. You see, because it's the sum around the mean. And that's the neat trick. That's why we subtracted from x bar, to make it a lot simpler. That goes to 0, and we're left with sum of yi equals na, so a is the mean of the y's. Is that okay? Does that seem all right? What we've done, is quite nice, is saying that when we fit this line, here's x bar here, and we're going to fit through y bar there. So the first data point, the intercept, it says the line is going to go through the point x bar, y bar. Makes sense, doesn't it? We just take the average. It's a sort of center of gravity of the points. The line is going to go through there. Okay, what's the gradient going to be? We have to take the derivative with respect to b. What do? We get the minus 2 again, but this time we've also got an xi minus x bar to multiply through the whole thing. So that comes up here, and we get a sum now of yi minus y bar times xi minus x bar. Oh yes, we know that that is y bar. So that comes down into there. That's it. That becomes y bar. And here we get a sum of b, and then we get a sum of xi minus x bar all squared. We set that to 0, move that underneath, and we get b as the sum of yi minus y bar, xi minus x bar, divided by xi minus x bar all squared. Nice, fairly straightforward calculation, which gives us the gradient. Now, I'm not going to make you do them by hand. That's what computer programs are for. So, but that's what it's doing. And when you fit using R, it's just using that formula to fit a straight line. For example, there. That's going through the middle of x bar and y bar, and it's fitting that gradient according to that formula. And it's the sort of best fitting line. Doesn't fit very well, does it? But it's sort of going upwards. Actually, it also looks like there's more variability as people get taller. I think that's, down here there's not much variability, and then it sort of goes outwards like that. So the data is perhaps curious. Okay, so we interpret that A hat is the intercept at x bar in the middle, and B hat is the gradient. We don't assume normality, but if we do, these are the maximum likelihood estimates. And if we do assume normality, the standard deviation sigma is just the square root of the residual sum of squares divided by n. Now, this estimate for the standard error is sometimes called the residual standard error. This is what R will use, I think, will give you that. It's slightly different, but it's just different in the denominator. All of these small changes are to do with small samples using things called t-distributions, which, as I said, we're not going to go into in detail in this course. I'm not actually going to cover that. We could do all that. It's just warning you that that's what's in the computer programs. It's all to do with small samples. Anything more than 30 observations really makes no difference at all. So as long as you've got about 30 observations, assuming the maximum likelihood way is fine. Okay, so we can fit those lines. And when you do it in the practical, there's a practical sheet, a PDF on the directory for afterwards, and some code. Actually, I haven't put it up. I must go and put it up for running these things. Okay. Now, one thing I did was look at that data point. Do you think that data point is correct? No. So I think the natural thing is just to take it out. And in the code, I just show how it's easy to remove a data point. And if we take it out and run it again, look what happens. What you would expect is the line I should have asked before, what do you expect to happen to the line? Yeah, well, what do you think the blue line, where will it go, do you think? You'd think it would get steeper. It doesn't. I thought it'd get more steeper, but it has some effect. The point is, this data point is being quite influential. You see, it's pulling that line up. One data point, one mistake, is having quite a big influence on the thing. And that's a real problem with mistakes in the data. They can be very influential. If that data point, if this one had been here, it wouldn't have much influence probably. But because it's down here, it's pulled up the curve. So we're getting a lot steeper gradient by removing the data point. Okay, then the other thing we can do is to start looking by gender. There's this scatter plot command in R, which I show you that, which I hadn't used before. And it's quite nice because it automatically will do it by gender and fit the lines for the two groups. So now we see this was a female. Tiny little female with huge hair. I may have typed it in wrong, so it's not, but it's a good example. So it's tiny little females, huge. And what this means, so what is the pattern for males? The pattern for males is quite what you'd expect. It'd go up big. The pattern for females now is being very influenced by this one point. So now we think that taller females, the taller the female is, the smaller their hand. And if they're really tall women, they're going to be tiny. So it just shows it's really good to look at the data. This is why you need to look at the data. If we remove that data point, it becomes sort of flat or slightly increasing. But there's not much data, so maybe those gradients are not really different. That's one of the things I should have asked. To see whether the confidence intervals around these gradients, maybe they overlap. Maybe there's not a real difference between males and females. We'll test that tomorrow. So, maybe there's no real difference there. Yeah, maybe there isn't. Okay, so that's what I'm going to be getting you to do. Is that okay? And I haven't put them up there, but part of it, of course, is to read the estimates off with their standard errors, to be able to find out what the gradients are, to be able to put intervals around them, and so on. Is that okay? Just one final thing is about logarithmic transformations. And I found this very nice example, which I think is really beautiful, on Gapminder. Okay. Gapminder is this program. Can I go full screen? Yeah, okay. This is the Hans Rosling, the mad, man jumping. I showed the video. He does these things. This Swedish madman. Okay, so this is quite an interesting one. This is for all the countries in the world, income per person, $20,000, $40,000, $60,000, $80,000, $100,000. God, who's that? Where's that? Average of 100? Qatar. The average income, $93,000 in Qatar. You can't believe it. Is that of everybody or just the citizens of... I can't believe all the visiting workers earn that. Luxembourg, look at that. Incredible. Singapore. Okay, and up here we got child mortality. The number of 0 to 5-year-olds dying per 1,000 born. Now, the crucial thing about this is that this is really difficult to spot the pattern. And it's not you wouldn't want to fit a straight line through that. But what this graph allows you to do rather nicely is to change the axis from a linear scale to instead use the logarithm of income. Whoa! And that spreads the points out. The point is that the distribution of income, if I just look at the distribution of income in the world, it's a hugely skewed distribution. So if I do income here, we saw that it's sort of like that, with a lot of countries down here and a few, Qatar, Luxembourg, Singapore out here. So if we take the log of income, it makes it a much nicer shape. Now, similarly for child mortality, if we take the logarithm of this, let's see what happens to that. Whoa. It's a straight line. Isn't that cool? It just turns into a really nice straight line, showing the progress of the spread across the world of these income. So that's that's just using logarithms, just transforming the data. We could suddenly start plotting that, fitting a straight line, and working out on average how an increase in per capita income is related to child mortality. The other thing I must show you, this is, let's see what's happened over history. Now, there's some places bouncing around here. We have Austria, France, 1828. Yeah, so France, this is Europe, 1850s. So it's all Europe. That's the only place there's any data for. 1830. Whoop, then there's some other countries. Here they come. But they're all up there. Here they come, First World War, it doesn't have that much effect. Oh, what's the big one? India? India, we've got some India data now, 1950s, they're still up there, and then suddenly, 1960s, China, 1990, 1999 to 2000, 2005. So they're all moving down together. So, and if you didn't use the log scale, that would be completely invisible, all that stuff. So, it just shows what a simple transformation, how it can reveal the picture. Okay, are there any questions on that? Alrighty. Okay, well, I'll go and load up the examples. Essentially, what you want you to do upstairs is to do some of this fitting. That's the old one. Just fitting straight lines and doing all that kind of getting the estimates out, everything like that. Okay? Cool. I'll go and load it up so you can download it. And there, as I said, there is a practical sheet. Oh, I know. Let me just have a look at that a minute. Here we are, which is just, okay, what do I want you to do? Down, make sure you've got data3.arc. Stop. This thing's doing things. There's some instructions I would like you to understand, like checking whether there's any missing data, where you use this is.na, and that checks about how much missing data there is. And then fitting the line using summary statistics, how to select observations, to remove the data point, scatter plot, etc., etc. So I hope that's okay. All right, I'll go and load the class.3 up. Right, thanks very much.